Okay, my name is Fredrik Heinz, and I'm a associate professor of computer science here at Linköping University, and I've been involved in algorithmic problem solving for actually, well, starting to get close to 25 years now, actually. Uh, so um, um, I've been competing in this kind of algorithm problem solving when I was a student in the late 90s. So actually, we were the first team to go to the Swedish championship in problem solving, and then my friends also went to the world finals in 2000, and then we started to run algorithmic problem solving contests here at Linköping when I started as a PhD student in 2000. Um, and then we've been running this course for, I actually don't know how many years now, 6, 7, 8, maybe 10 years actually. I don't really know. So I think it's a really nice endeavor. Um, as I said already, the outline of today's lecture is that we're going to talk about what is algorithmic problem solving, why is it important, what are the course content, what are some kind of just overview of a large number of different methods that we will be discussing more in depth in this course, and also a bit about common approaches. So first of all, what is algorithmic problem solving? So algorithmic solving problem is all about solving problems where the solution to the problem is in the form of a program. So rather than you manually solving a problem, for example, in math, you do the calculations and you reach an answer and then you're done. Here, what we're interested in is to write programs that solve classes of problems. So instead of just solving one math problem, say a linear equation system, you write a program that can solve any linear equation program, which is actually one of the labs in this course. And in order to do this, we're also interested in that it should be correct, meaning that it should solve every case or every instance of this class of problems. It's not about solving 95% or 99%. It's about solving every case or sorry, every instance in the class. So that's a very important part. In order to actually make this achievable, it means that we are working with a specific type of problems, namely those that are very well defined. So all the bounds are known in advance. We know exactly how large these problems can be. And we also can assume that there actually is a solution. We are not trying to solve problems which are unsolvable. But of course, it can still be very hard. So it's some sense the intersection between three different areas. So we have the kind of algorithms, the kind of theoretical parts. So for example, this construction and analysis of algorithms course is mainly a theoretical course studying different algorithms and their properties. On the other hand, we have programming, so basically how to write programs. And then we have this problem-solving aspect, how to take a general problem, how to break it down into smaller parts, how to identify the key dimensions, and so on and so forth. That's the problem-solving part. And this algorithmic problem-solving course is then in the intersection of these three areas. So let's see. Yeah. So there is another thing that which is very important, and that it should not only be correct, but it should also be fast, meaning that it's not only sufficient to find a working solution, but it also has to be fast enough, solving even large, or I mean, yeah, the largest instances, the hardest instances in these classes within a very limited time, which means that this time and space complexity, more time than space complexity, is very important for solving this. And it also means that testing is very important. To simplify in some sense, or well, to determine whether you've actually solved the problem or not, we will use automated testing, which includes a large number of test cases, which have been designed in order to make it very likely that you actually solve every instance of the problem, and that you do this fast enough to make it sufficient. So it means that you have to do it correct, you have to do it fast, and you have to solve every instance. So why is this then important? I find this kind of legacy slide. I think this is like eight years old at least, but it's really about the fact that that kind of software is eating the world, as the slogan goes. After Mark Andreessen, who said this a number of years ago, basically that, I mean, previous things that were done by hardware is now done by software. For example, I usually use Ericsson as an example, where they previously had like customized hardware in the base stations. Today, it's basically some kind of Unix, Linux computer, and just change the software, and then you get new functionality in your telecom network. Tesla is another example, which is basically just a simple, a computer on wheels. So by changing the functionality in the Tesla, you just change the software, and it also means that they can, of course, collect data about how people actually drive, and then change the behavior based on how people drive and improve the product continuously over time. So what we see today is that more or less most of the value provided in products are actually provided in the form of software, which means, of course, that those that really understand and can take advantage of software technology will own the future, maybe more accurately, actually invent and develop the future. And of course, this was also one of the reasons why we started this 5-year engineering program in computer science, software engineering, mjukvaruteknik, and that was also when I created this slide. So I really think that the topics of this course is really the core of what you need to know to be successful in this industry. So, for example, if you want to have a job at Spotify or Google, then these are the exact skill set that they are looking for. Being able to solve algorithmically challenging problem at large scale with guarantees of being correct. So that's why I think this is a really important course in that respect. Then, of course, we also have programming competitions like the International Collegiate Programming Contest. And of course, it would be great if Linköping could have a team in the World Finals. Unfortunately, the competition is really, really challenging there, but at least you should never give up the hope. So you see that it's mostly Russian, so it's either Russians or Chinese that usually win this. Anyway, so what are then the types of problems that we're working with? If we have had a normal lecture room, I would have asked you how many people have solved this kind of problems before. Now it's kind of difficult, especially since we actually have a large crowd here today. But the type of problems that we are solving are the ones shown here. Basically, it's a problem statement that fits in 1 or 2 A4 pages. It always has the same structure. There's like a background, there is the kind of formal definition or the kind of the detailed description of the problem. There's detailed descriptions of the input, the output, and then examples. So the background and the problem describes what should be done and kind of gives you the information you need in order to understand what the problem really is. And then there's the exact specification of exactly what is the input and exactly what is the output. And in here, you should really keep in mind that you should do exactly what it says. It's very important. So if there should be an extra empty line at the end of the output, even though that's not very common anymore, then you should actually have an empty line at the end of the output. Otherwise, it might be considered incorrect. And then these examples will be very important, both to kind of test your own understanding of the problem, but also to test your potential solutions to the problem. So these are really important. So if we look at this particular problem, it's the first problem on the UVA problem solving site. So it's called a 3n+1 problem. And here it basically, it's a certain class of problems, blah, 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 blah. So basically it's given an algorithm to compute this. So basically you multiply n by, so you check if n is 1, then you're done. If n is odd, then you replace n with 3n+1. If n is even, you divide it by 2. So it means that and then you kind of iterate this process over and over and over. And then you get for a particular input number, you get a sequence of numbers. For example, for 22, since it's even, we divide it by 2, we get 11. Now it's odd, we multiply by 3 and add 1, so on and so forth. And then we get the sequence. And then there is a conjecture that this algorithm will terminate for any integer input. And then what you're supposed to do is that given an input n, it is possible to determine number of numbers printed before and including the 1. So for a given n, this is called the cycle length of n. In this example, the cycle length is 16. For any two numbers, I and j, you are to determine the maximum cycle length over all numbers between and including both I and j. So here is then the description. So I guess that's quite obvious what you're supposed to do. And then you get the inputs. Yeah, so you know that there are two integers. They will be less than 10,000. They will be positive. And you should process all pairs of integers. And then the output here should, you should output them in the same order that they were written, and I and j should also be in the same order. And then you have the sample input. So this is then an example problem. So in this case, to solve this, you basically need to follow the instructions. You basically need to implement this algorithm. Then you can use a number of techniques. For example, you can store, since for each number, I mean, you know this maximum cycle length. So basically you can pre-compute, or at least if you compute it, you can store it. So you don't need to compute it once more. You can actually, even since it's just 10,000 numbers, you can just create a table of all 10,000 numbers, and then you can solve this problem in constant time. So you do everything pre-computing. And then this problem is interesting because it has a number of gotchas. For example, that the order between I and j is any, which means that j can be smaller than I. They can also be equal. And you have to print them in the same order. So you cannot just replace I with the smallest of I and j or something like that, but you need to actually create new variables. So this is then a good example of a problem that, even though it's very simple to get a solution, in order to solve it really, really fast, there are a number of improvements you can make, and there are a number of things that might be easy to overlook and therefore incorrect solution. So what is then the course goals? The kind of course goals is that you should be able to analyze the efficiency of different approaches to solving a problem to determine what approaches will be reasonable, efficient in a given situation. So this is basically trying to figure out which solution or type of solution works for what type of problem. You should be able to compare different problems in terms of their difficulty. So one of the parts in the course is what we call problem-solving sessions. And in these problem-solving sessions, you're given a problem set. We will use 6 problems, and then you need to solve them. And basically, you should solve them in order of difficulty, so that you solve the easiest problem first. Because if you start with the wrong problem, start with a hard problem, you might not finish even one problem. So therefore, determining the difficulty of these problems will be very important. And then you will also learn to use design techniques, algorithmic design techniques, such as greedy algorithming, dynamic programming, divide and conquer, combinatorial search, and so on, to construct algorithms to solve given problems, which means that in many cases, there will be any kind of existing algorithm to solve a problem, but in many cases, you will need to change, tweak, or even create new variants of these algorithms to solve these problems. And as I said, it's not only enough to kind of select the right algorithm, you also have to have a correct and working implementation. So therefore, you will need to learn strategies for testing and debugging algorithms and data structures. That would be a very important part. And since these problem-solving sessions are timed, it means that you have limited amount of time to do this. You also need to quickly and correctly implement a given specification of an algorithm or data structure. So really getting the speed up is crucial if you want to be able to solve many problems at these problem-solving sessions, or for example, if you want to compete, then I think, I mean, in some sense, to do reasonably well, at least in the kind of Swedish or Nordic context, as long as you know the standard algorithms and you can implement them very quickly, then you have a good chance there. And then most of these will be done individually, but there will be 2 problem-solving sessions where you work in teams of up to 3 people. And so also communication and cooperation is one part of this course. Because I mean, in real life, of course, most of the time you will be solving these kind of problems in teams. You will not do them by yourself. So this is another important skill, and also to kind of have complementarities, and especially if you're putting together a team for a competition, then you should find ways of how to get the most out of 3 people, but only 1 computer. So these are then the course goals. The examination, there are 2 parts of the examination. So there are labs and the problem-solving session. So that's the kind of major part. So there are 4 lab assignments. And for each lab assignment, there will be an individual problem-solving session. And then for each term, I would say period. So after the first half of the spring, there will be a group problem-solving session on the first 2 labs, and then at the end, there will be a problem-solving session on the last 2 lab assignments. So the purpose here is that in these problem-solving sessions, you will benefit from having done the labs, because you can use the code to solve the problems, which means that the more labs you have completed, the more better chance you also have in the problem-solving sessions. The second part are weekly homework exercises. So every week there are a set of problems that you should solve. You don't need to solve all of them. You roughly, I think you have to solve like 1 problem every week to kind of pass the course, and you have to solve like more than half, like 3 or 4 every week to get the highest grade. So this will also be an important part to practice throughout the course and to cover different topics. So here is the schedule. I will not read all the details, but basically we will have every Friday, or there is 1 or 2 Wednesdays as well, there will be a seminar. So in this seminar, the first hour, or actually only the first hour, will be live, so to speak, where we will discuss the week's problems. So we will go through in detail how to solve the problems, which of course is very good if you haven't solved them already, but also if you have solved them, then you will learn about how finding different ways of solving it, because most of these problems have many different ways of being solved, which means that you will always learn. So I think this first hour of the seminars will be very useful for most of you. And then there is a lecture part. Now that we're in distance mode, this lecture part will be pre-recorded. So at the latest of the day of the lecture, the recording of this lecture will be published. So since we were in distance mode the second half of last year, actually the second half of the course already have the lectures recorded. So I will record the first half of the lectures as well. So, but there will be the first hour of the seminars will be live. And we will also be expected to discuss your how you solve the problems. So if you continue to be 70 people, which I think is really great, then we will split you up in breakout rooms to facilitate the discussion. Yes, So that's all the details. Okay, so that was a overview of the course. Now I will spend the last 20 minutes here talking about how to solve algorithmic problems. So in some sense, the first part, or maybe I can ask if are there any questions on the course, yeah, the course itself or anything. You can either speak or you can write in the chat.
Yes, I have a question. Where are the recorded parts? We got a mail saying that the second half was finished.
They're on
Are they going?
the lecture page. So
All right.
there are links to YouTube recordings. So everything is on the course webpage under yeah, lectures and seminars. So there are also the slides that I present.
Which programming language do you recommend?
Well, I mean, I recommend, I mean, C++ or Java is usually the best. Well, my personal favorite is C++. That's those two languages are guaranteed to be able to solve every problem there is. Python can be a very useful language in many cases, but there may be problems, for example, where there's a lot of I/O or things like that, where Python is just too slow. But you are allowed to use any programming language which is accepted by CATIS. So you have a lot of freedom, but my recommendation is C++ or Java.
I have another question.
Yep.
Would it be all right if you could upload the current slides in advance of the seminar or the lecture? Because
They
there's
are
a
already
link to
there.
the old slides, and for instance, the schedule was off. Otherwise, yeah, it was pretty much the same. But I am taking notes in the actual lecture page, and it would be nice if they would they were updated in advance.
Well, yeah, well, well, normally, well, actually, in this case, it will be simple because there will be no, this will be only live lecture. Normally, there is always a tendency to make changes, so therefore, I usually upload the slides afterwards. But I see your point, and I mean, yeah, I don't expect any major changes. So the old slide should be very close, but yeah, the schedule, of course, is different. But I would try to keep it in mind. So there was a question about solving one problem before the seminar or just whenever. So basically, you can solve the problem whenever. If you solve them before the seminar or up until the seminar, you get full points for that solution. If you solve them after the seminar, you get half the points. And the reason is, of course, that we want you to learn from the seminars, but that you should get a benefit if you solve them in advance. So it means that you should try to have one solution before the seminar every week. That's very good. But you can solve them afterwards as well and still get some credits. There's also a question about, is there a possibility to see the test cases to get more help? And no, that's not the case. And actually that's by design, because you should be able to come up with test cases yourself. So actually this is one major debugging strategy, is to create complicated, what you think would be complicated test cases. If you really get stuck, and I mean really have been trying, then you can contact the lab assistant, Herman, and he can provide you with a specific test case. But this should not be the first thing you do, but rather if you really get stuck. Okay, more questions? Oh, well, if you come up with questions, just type them and I will answer them. Okay, so now it's the how to solve these kind of problems. So the first thing is, of course, to estimate the difficulty. Is this a hard or an easy problem? And in order to determine this, there are a number of things you could look at. For example, theory. So here, one thing to look at is the input. I mean, the larger the problem instances are, the more efficient solutions you need to find, or efficient algorithms you need to find. Can you map this to some known algorithm? Of course, that also makes it easy. So sometimes a problem could be really, I mean, hard in some sense. But if you have solved it, I mean, if you identify the correct algorithm and you know exactly how it works, it might be a simple solved problem for you. Sometimes there is a need to kind of rewrite or to reformulate the problem. Maybe there is some known theorem which allows you to simplify the problem. You can analytically solve some parts. So that can also help. So in some sense, the less you you know about the problem, the harder it probably will be. And then the second part is the coding. So sometimes problems can be really easy to understand, but it can still be very tricky to implement. It could, for example, be that there are many cases that you need to care about. So, for example, computational geometry is usually this nature, or it could be that it has floating point numbers that usually also can make things more tricky. You need to care about error propagations and roundings and all these things. And sometimes it's just that you need a complicated data structure. But on the other hand, you might have solutions already. For example, take max flow or something like that, which is very common. That if you haven't implemented max flow before, it's probably not something you will do in 10 minutes. But if you have an implementation of it already, then solving a max flow problem might just take a few minutes, because you just copy the code and then you generate the graphs and then you're done. So this is another aspect of actually implementing it. And if I were, I mean, my experience, especially when it comes to competitive programming here at Linköping, is that I feel that many students and many teams, they manage to understand what is the right algorithm. They kind of get the theory part right, but they're too slow and too much errors in implementing it, so that it just takes too much time. So I think this is one difference between those teams that are okay and those teams that are good, is actually doing it very quickly and very correctly. And I can take an anecdote here from Jimmy Modell, who was one of the best people in kind of competitive programming when I was competing 20 years ago, and who now works at Spotify. He's implementing their distributed playlists and so on. And he said, so what separates you from other programmers? And what he said was, well, I do it correctly the first time. And I really think that's important. He saves a lot of time by not making mistakes. That is, and of course, he was also one of the fastest in solving these problems. So that is really an advantage, to do it correctly the first time and to be quick, still be quick. And then there are other aspects, like, have you seen the problem before? That's very important. Have you solved it before? Do you maybe even have a useful code in your code library? So developing this library of algorithms and partial solutions will be an important part to also speed up your work. So that's the kind of first step in order to understand the difficulty. Then now you have an understanding of the difficulty. Now you want to solve the problem. And then the first step is, of course, understanding what the problem really is. So what is really being asked for? That's crucial, of course. What is given? So what is the information you have? And here, a good advice is that usually, since these texts are very condensed, if there is information if they're, for example, saying that, I don't know, there's some piece of fact in there, most likely that piece of fact is significant. And then the third part is, like, how large can the instances be? So this is probably the first thing you look at, because that will determine what algorithms maybe you can use. and then you might draw diagrams to help you understand the problem. So actually there is a book by Polya about how to solve it, where a lot of these things come from. So that's a book that I can recommend, which talks about how to solve problems. And he then used, I mean, can you draw a diagram to understand the problem? Can you explain the problem in your own words? So this is a technique which is very useful, especially if you're working in teams, that if you get stuck, you try to explain for someone else, what have you tried? How do you understand the problem? Why is this a solution? And so on. And quite often this gives you some hints on how to proceed. There is even the rubber duck method, where you put a rubber duck or some other thing, for example, on your monitor, and then you talk to the rubber duck and try to convince the rubber duck that you know what you're doing. And just by saying things out loud, you often come up with new ideas. And then so related to this test case question, then I mean, try to figure out what is the smallest hard problems and what are the largest hard problems. For example, what case would generate the kind of worst case complexity? Or if you look at the actual way that code is written, what would be worst case examples? And then try these. So that's another important problem. So there's a question on, when you're supposed to solve a problem by yourself at a limited time, what happens if you don't complete the task in a given time? So it's only during these problem solving sessions where there is a, I mean, meaningful time limit. Of course, there is always a, I mean, so then for the problem solving sessions, only those problems solved within the time allocated will count. But for the kind of exercises and for the labs, you basically have as much time as you like. If you solve the exercises before the seminar, you get twice as many points for it, but there is no real time limit there. Okay, so now you hopefully understand the problem. Then the next part is to determine the right algorithm or algorithmic approach. And here, usually, I mean, this is in some sense an ordered list of things that I recommend. So that can you solve it using brute force? So basically, trying every possible combination. So in some cases where the problem instances are so small, even though there exist very efficient algorithms, usually brute force is much quicker. So think about that. The second is using greedy approaches. So basically trying to do local optimization to get global optimal results. Often, for example, if it's an optimization problem or something like that, then dynamic programming is a very good solution. So basically, if you can formulate a recursive definition of the solution, then translating that recursive definition into dynamic programming solution is usually straightforward. And a bit more formally, dynamic programming is useful when you have need to recompute the same thing multiple times. So then you basically avoid doing this recomputation by storing the computed value. So only compute each value once. So that's a very, very useful technique. Then search is another general approach which allows you to solve most problems. So here the question is, of course, coming up with either a which kind of search you want to use, depth first, breadth first, A star, so on. Or more likely, you probably need some kind of heuristic search. So you need to limit the search space by adding a bit of knowledge, and then you can solve a large number of problems. So what we have seen in kind of competitions the last number of years here is that probabilistic search methods actually have started to work, which means that you're not guaranteed to find a solution, but most often you find it. So then you can actually submit several times, and hope that one of the solutions will solve it using different seeds, for example. And then if there is a known algorithm, then you can use it. Otherwise, you might need to modify an existing algorithm. Sometimes you need to modify the problem. This is often the case to use as these kind of max flow methods. So max flow is extremely general method, but you often need to formulate the problem into a flow problem, and you can just reformulate the problem, then you can apply max flow. And then in the kind of worst case, then you have to come up with your own algorithm, but that also happens. So now you have figured out what the right approach is. Now you just need to solve the problem, which of course is easier said than done. So this is a kind of a general outline of the process of solving it. So there's a question about the grading. So basically the grading, so you can read it on the web page, the course web page under examination. So basically you collect points. So the more exercises you solve, the more points you get for this UPG1. And then there is a threshold, so you can see exactly how many points you need for the different grades. And then the same for labs. So there you add the points you get for solving the labs, and you add that with the points you get for problem solving sessions. So then you get a grade for the labs and a grade for the exercises. And then there is a table for how to combine this. So since so you get the overall grade for the course. So since the labs are twice as large, they're 4 credits compared to 2 credits for the exercises, that carries more weight. So for example, so if you have a grade 4 on the labs and grade 3 on the exercises, you will get the grade 4 on the course. So all the details are on the examination page. Yes, so then this table is very important and very good to keep in mind. So I've alluded to this, that for each problem there is a time limit, which means that there is a maximum amount of time that you have for your program to solve each instance. So usually, I mean, I think very normal time limit is like 1 second. Maybe in some cases it's more, but it's just a very short time at least. And the assumption that you can make is that you can do about 100 million operations. So this is a very good rule of thumb, that if you can solve the largest instances of the problem with at most 100 million operations, then you probably should be within the time limit. This is just a rule of thumb, so it can be a bit more, a bit less, but this usually works. So then we can see just by looking at the dimensions. So assuming that we have an algorithm which has a complexity in one variable, so usually there is like a main variable. So if if n is like 10, 11, then we can use n faculty solution. So for example, every permutation, we can try every permutation of something that's order n faculty, which is actually the same as order n to the power 6. So even a relatively low polynomial can only do 10, 11 instances of that size. If we have slightly larger problems, so now, but we still relative 15 to 18 elements, then we can do dynamic programming traveling salesman. So we can both have a exponential term, so 2 to the power n, and we can do this n squared times. So basically having a 2-dimensional matrix, and for each filling in each cell, we can then spend exponential time. If we can have, if we remove, so we only do this once. So for once, for every n, we compute something that takes exponential time. Then we can do like up to 22 in size. So this is, for example, dynamic programming with bit mask techniques. So we store multiple instances in a bitmap vector. If we now get down to 100 or get up to 100, then we can use n to the power 4, which means that we have basically can do a loop, 4 loops, or we can have 3-dimensional dynamic programming with an order n loop. So we can go through this once per element, and so on. 450, now we can do, for example, cubic algorithms like Floyd-Warshall's all pair shortest path methods. If we're 2000, now we can do n squared log n. So for example, that corresponds to 2 nested loops plus a tree search to get the logarithmic term. If we have 10,000, we can now use all the n squared algorithms like inefficient sorting methods. If we get to 1,000,000, now we need to do n log n. So actually, I would say that n log n is a very common kind of complexity, because then you have a kind of one outer loop and then some tree search within binary search or something like that. So for example, most computational geometry problem are n log n, and of course searching. And then if we have even larger instances, then we have to have a linear algorithm or logarithmic or constant algorithm. So this gives you a sense, by identifying the main dimension, you can limit what type complexities you can actually solve. So this is kind of very important to keep in mind. And then there is a large number of problem-solving methods. I will not go through them here, but we will go through them in the course, and all of them are useful. Also, data structures is of course very important. So you should really get to know the standard library data structures. So exactly how to write this will of course depend on your programming language, but these are extremely useful and of course simplifies the work very, very much. And then there are a number of data structures that you need to create yourself, like graphs, segment tree, Fenwick tree. Fenwick tree, for example, extremely useful. Tries if we're working with strings and so on. So those you need to implement yourself or find good implementation that you learn. Sorting strings will also be important. So yeah, here's just basically a enumeration of a lot of the things that we will go through in this course. So there are a lot of things. So it's a good thing just to check off and see what are the things you already know, what are the things you that's completely new, and so on, and what you need to learn more about. So to kind of conclude, we also have this, all the problems are solved within the CATIS automated correction system. So this is originally developed by KTH, and we have been using, so all the problems are here. Now it's 21, so it should be APS 21 instead. There's a link on the webpage. So you basically join the course, and then you find all the exercises and all the labs there. And this is also where the problem solving sessions will be. So it's good to understand how CATIS checks a program. So when you submit a program to CATIS, first of all, it tries to compile it. If it cannot compile it, you will get a compilation error. If this was a competition, you wouldn't get any minus points for this and get any penalties for this. After it has compiled, it will then run the program once, will run the program for each test case. And if it crashes, then you will get a runtime error. If it takes too much time, you get the time limit exceeded. If it finishes in time without crashing, it checks is the output correct. If the output is not correct, then you will get the wrong answer. If it solves that test case, it will then go to the next test case. And if you get the right answer on every test case, then you will get accepted. So this means this is how to kind of interpret the output of CATIS. We also, There's also this online judge, which we use, for example, for this IMPA contest, the IDA mästerskap i programmering och algoritmer, which is a algorithmic problem solving contest, which we also run. So that can also be useful. Yeah, so here's some question about the programming languages. So here it says that allowed languages are, so that's kind of old. I would say that all the languages that are accepted by CATIS are allowed. So, and as I said, I recommend Java or C++. And it's important that input and output, that some problems require a lot of input and output, and then you need to speed things up. And of course, to learn your language, learn your tool. There's a question about, is there a limit to the number of times you can submit to CATIS? No, there is no limit to the number of times you can submit to CATIS in the course. In a competition, you usually get a penalty for every incorrect submission, but that is not applied in the course. Yeah, and here's just a template that I've used. I mean, people usually have a lot of type defs to speed up creating different data structures, but I haven't done that here. And then testing and debugging is very important. So you should always create these input and output examples so that you are at least sure that you solved them. And then you probably should create additional tests, such as extreme inputs, like the smallest and largest values. That's easy to do. Small inputs that you can compute by hand is also very good. If you can come up with especially tricky or hard cases, this is also good to add. Sometimes if you need very large cases, this is usually hard to do by hand, but then you can randomly generate them. Writing a program that generates inputs for you, then you can check that to, for example, how it scales up to large problems. Sometimes you might be able to find a slow algorithm that computes the correct answer. Then you can use this slow algorithm to verify your fast algorithm by computing the correct answer to the test cases, and then you can verify that your solution finds these. Debug outputs is something very useful to use as well. One of the main methods to understand what's going on. So in summary, what I've been talking about here today is what is algorithmic problem solving, why is it important, what is the course content, and then I've been talking about the kind of general approach to algorithmic problem solving, and a little bit about CATIS and debugging of problems. So that was all I wanted to present today. Let's see. So here's a question. Do I understand it correctly that you don't necessarily need to attend all problem solving sessions? Does it matter which sessions you attend as long as it's at least 2 individuals and 1 group? So that's correct. So in some sense, the only, well, put it this way, it's only the problem solving sessions which is in some sense mandatory. But since only the 2 best individual and the best group problem solving session kind of counts, it means that you actually have twice as many opportunities as you need. So if you're satisfied after, for example, doing the first 2 individual problem solving sessions, you get enough solved problems there, you don't need to attend the last 2 ones. So there is no, so you can attend any subset that you wish, but as long as you complete at least 2 individual and at least 1 group problem solving session. There were also a question earlier about whether I would recommend or whether it would be okay to create kind of a discussion forum for discussion problems. So I think this is a very good idea. So if you create such a discussion forum, you're more than welcome to invite me and the lab assistants, Herman and Fredrik, and we will also try to answer questions that you might have. So I think that's a very good idea. There's a question, will there problem-solving sessions be during the lab time in the schedule? Yes. So they are scheduled. So I think they're usually on Thursday afternoons, I believe. Oh, so then we see that there is always a Discord server created. Excellent. There's also a question, just to verify, you're allowed to use the code for labs and exercises in the problem-solving sessions? Yes, that is not only allowed, but actually recommended, that as part of the solving the labs and solving the exercises, that you basically create a code library, and that you use this code library to simplify solving the problems during the problem-solving sessions. Will the groups be randomly assigned? Normally, we have allowed people to form their own groups. There could be some positive things with the randomly assigned groups. So I will not give a definitive answers, but historically, we have allowed the students to select their own groups. Okay, any more questions? Okay, then I thank you all for today, and I'll see you again, or I don't really see you, but we will have our next session on Friday. Let's see, on Thursday afternoon, there's the first lab, and the first lab will be used as a kind of practice problem-solving session. So it will be like a problem-solving session, but it does not count towards the grade or anything. So it's just for practice, so that you get a feeling for it. And Herman sent out instructions for that earlier today. And then on Friday, we will discuss the first set of exercises. Okay, so with that, I wish you all a great day, and see you on Friday.